Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamburu. Welcome. Today we'll be revising. We'll be dealing with the knowledge area, electricity and magnetism, which is the knowledge area that you dealt with in grade 11 and is part of our exam. So I'm hoping that you will be able to do well in terms of this particular topic. And then, with no wasting of time, we'll be looking at the lesson objectives for this particular lesson to see what are the objectives that we would like to reach the state Coulomb's law, which is the first thing, and then that is the first thing that we'll deal with, which is what is to state what is Coulomb's law. I know you have done it in grade 11, but it's important that you collect as many marks as possible, more especially topics like this one under this knowledge area of electricity and magnetism. Now we are saying Coulomb's law. It says the magnitude of the electrostatic force exerted by one point charge on another charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. It is much easier when you take it from the equation itself, which is F equals to K, Q1, Q2 over R squared. So if we remove the proportionality constant there, we'll have F directly proportional to Q1, Q2 over R squared. So when we are simply saying state Coulomb's law, definitely you will refer to that equation where you will say the F there stands for the magnitude of the electrostatic force. So that is the magnitude of the electrostatic force exerted by one charge on another. So that's what you are saying. You are saying the magnitude of the electrostatic force exerted by one charge on another charge. So charge Q1 on charge Q2 is directly proportional. It's directly proportional to the magnitude of the charges. So it means as the charges increase, the electrostatic force will increase, directly proportional. But we are saying and inversely proportional to the square of the distance between them, which means now when the distance increases, the electrostatic force will decrease. Remember, we said when it comes to the magnitude of the electrostatic force, it's directly proportional to the magnitude of the charges, where Q1 and Q2, and is inversely proportional to the square of the distance between them. So always have that and remember how to state Coulomb's law. In terms of this question under electrostatics, you will see that the most important definitions that we're expecting you to remember is Coulomb's law, is electric field at a point. So as one of our first objective is for you to be able to state Coulomb's law. And we're saying always remember we're talking about the magnitude of the electrostatic force that we are saying exerted by one point charge on another point charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them. Now we're going to use this equation of F equals to K, Q1, Q2 over R squared to solve problems using this equation. So we're going to use this equation to solve problems. And we're going to deal with charges that are in one dimension. We're only restricting to 3 charges here. So you will see we're talking here about Q1, Q2, and Q3, for example, but they are all in one dimension, so on a straight line like that. So we'll be able to solve them. We're not saying the straight line, they must be horizontal, it can be vertical, but as long as they are in one dimension, we're simply saying when they are horizontal or when they are vertical. So we're talking about the one dimensional there. So we must be able to solve those, and we are only restricted to 3 charges. So we want to have a situation where we give you more than 3 charges. It will only be maximum of 3. The other one, we're going to solve problems for charges in 2 dimensions. And even here, we're referring about the right angle triangle formation, and we are still limited to 3 charges. So we're still limited to 3 charges, and we are limited to 3 charges, and we can form a right angle triangle there. So that's when you are having a charge, another charge, and the third charge there, and the 3 are making a right angle triangle there. So you are able to see that Now we're going to deal with those two scenarios. The first one being charges in one dimension with a maximum of 3 charges. The second one being charges in 2 dimensions, and then we're still restricted to only 3 charges. So we won't have more than 3 charges. So those are the first objectives that we're going to achieve for today. Now, Coulomb's law, just a background there to say, remember, it's Charles de Coulomb who investigated the force that charges or charged objects exert on each other. Hence, we call it Coulomb's law. Now, we are simply saying here now, if you are having like charges, like you are having a positive and a positive, they will repel. But if you are having unlike charges, Q1 and Q2, the other one is positive, the red one is positive, the blue one is negative there. You are able to see that unlike charges, they will attract each other, which means they will have an electrostatic force of attraction. Language is important. The force between them is electrostatic force, and it's the electrostatic force of attraction. But when we are having like charges, for example, if we are having a positive charge and another positive charge, so those are like charges, and you know what the like charges do, they will repel each other. So that is the concept that we are going to deal with, to say when we are having 2 charges, there's going to be electrostatic force. That force can be force of attraction or force of repulsion. So that is important, and that's what we're going to focus on. Now, we're going to look now at the electrostatic force experienced by the object. This, remember what we said. We said the electrostatic force, which is F, we said is directly proportional to the product of the charges, which means Q1 times Q2. So it's the electrostatic force is directly proportional to the product of the charges. Hence, we are saying like that. So what does that mean? It means as we increase the charges, we increase the electrostatic force. As we decrease the charges, we decrease the electrostatic force. Now, it's important, we're having a graph there. Remember, we're taking this from F equals to K, Q1, Q2 over R squared. So now, if we were to draw the graph, of F versus product of charges, the graph would look like that. You will see that the F now is on your y-axis, which is now, and you are saying Q1, Q2 is your X. So on the X, we are having Q1, Q2, and then, which means that we are having now your gradient as your R there. Your R will be remaining constant in terms of that one. So the third variable, we're keeping it constant. So we're saying you are having your force, which is on your y-axis, and the product of the charges, provided that the distance between them remains the same. So you can see the relationship between the force and the product of the charges. The main thing is that as the product of the charges increase, you can see the force is increasing. Hence, we're saying that relationship is a directly proportional relationship. So if you were to draw the graph, you will draw like that. Don't forget, provided that R remains the same, or R remains constant, which is the distance between the charges. You will understand that as the charge come closer to one another, we are simply saying that now it will affect as well the force. So hence we are saying let one R be constant, so that we can be able to look at the relationship between the force and that one. And that question is an exam question, more especially in multiple choice questions. You will get questions where we'll say, what will happen if we double the charge? What will happen if we double Q1? So you will say, if we double Q1, what will happen to the force? What you do is simply to write the formula F equals to K, Q1, Q2 over R squared. You substitute the 2 there on the formula, you will be able to get K 2Q1, Q2 over R squared. So you can see you have a 2 there, you can take it out, and then you are getting 2 KQ1, Q2 over R squared. So you can see that, the force will be doubled, because you know that this is equivalent to the force. So you're able to see that if we double one charge, we'll double the force. But now, what will happen if we double both charges? The same will happen. You will go and say, okay, F equals to K. We're doubling both charges. You'll say 2Q1 multiplied by 2Q2, because we have doubled all of them. That is over r squared. And 2 times 2 is 4. So we can take out the 4 there. You will have 4 equals to, F equals to 4 K Q1 Q2 over r squared. So you can see that K Q1 over r squared is F, which means the force now will be quadrupled, or will be 4 times more. So you can see that if we double both charges, the force will as well will increase by a factor of 4. So it's very much important that all the time you use the equation so that you're able to check the impact of doubling or of increasing the charges on the force. So we've demonstrated here that as we increase, or as we increase the magnitude of the charge, the force will as well increase. Hence, we are saying that the electrostatic force is directly proportional to the product of the charges. I hope you have that. Now, if you look now on the relationship of the electrostatic force and the square of the distance, r squared. What is the relationship? We have drawn a graph of F versus r squared. You can see on the y-axis we are having the force there, and then on the x-axis we are having r squared, which in this case is 1 over r squared in terms of the inverse of that one. Now you are able to see that as well here we are going to have r squared and we are going to have the force. So what is the relationship? You can see the relationship that as the r increases, the force is decreasing. So can we demonstrate that? Yes, we can write the formula F equals to K Q1 Q2 over r squared. Let's say we double the distance. We double the r. If we say 2r, you are going to substitute there the 2r, which will give you K Q1 Q2 over 2r. Remember, the whole of it must be squared. So it's 2r squared. That will give you 4r squared, which means now we are having K Q1 Q2 over 4r squared. We can simply remove the 1 over 4 there, and then you will see we'll have 1 over 4 K Q1 Q2 over r squared. And then you are able to see that it means now when we increase the distance between the charges, the force will decrease by quarter, by that factor 1 over 4. So you can see that as we increase the distance between the charges, the force will decrease. But it is exponential, hence the graph is not a proportionality one. It is inversely proportional, and you can see that it's exponential because it's r squared. It doesn't mean that as you decrease or as you increase the distance, you double it, it won't decrease by 2. It will decrease by 2 squared, because the distance is squared. The relationship is inversely proportional to the square of the distance between them. So when it comes to the distance, it must be squared. So it means when we double the distance, the force will decrease by 1 over 4. And then if we multiply the distance by 3, it will be 3 squared, which means that our force will decrease by a factor of 1 over 9. Please always remember that as and when you do questions, and this relationship is important, as well as these graphs. I hope I've instilled that in you, and you can see it's clear that you can be able to do that. Now, as we continue with electrostatics, we are saying force is a vector quantity, so the direction of the force must be indicated. So it's very much important as you are dealing with forces, that these forces, they are vector quantities, so they have magnitude and direction. Remember, always when we are dealing with forces, we'll talk about the magnitude and the direction. And we are saying attracting, if the charges are unlike charges, we have attraction. Attraction is where we talked about it. Unlike charges, they attract, but like charges, they repel. And they repel in accordance with the Newton's third law. Remember Newton's third law, we're saying if an object A or an object 1 exert a force on object 2, object 2 will exert an equal but opposite force on that object. So they will be equal but in opposite direction. So the force exerted by body 1 on body 2 will be equal to the force exerted by body 2 on body 1, but in opposite direction. And then the other thing which is important is the issue of the net or the resultant force, which we are saying is a single charge can be obtained by a vector addition of all the forces acting on the charge. So always we'll ask you to calculate F net. And we're saying when you're doing F net, take direction into consideration. What does that mean? It means if F1 and F2 are moving in the same direction, definitely they will all be positive. But if they are moving in opposite direction, the other one will be positive, the other one will be negative. Hence, when you are dealing with the issue of F net, the direction is of paramount importance. I hope you will apply that as we're going to deal with questions after this. Now, this slide is there to show to you. We said we're going to restrict ourselves to maximum of 3 charges. So you can see that these charges are in one dimension, and we restricted ourselves to 3 charges. Sometimes we just give you 2 charges, Q1 and Q2, like that. Sometimes we'll give you 3 of them. So it's important to know that we can deal with 2 charges, we can deal with 1, 2, or 3, but a maximum of 3, not more than 3 charges. And when you say they are in one dimensional, I've already said it. They will be horizontal or they will be vertical. So don't be confused when you go to a paper, you are having Q1 and Q2 given like that, in that way, and then you are saying no, they must be horizontal all the time. No, we're saying one dimension, it means it will be either horizontal or vertical. But when you say 2 dimension, we are saying we have both horizontal and vertical. Hence, we are saying it's 2 dimensional. And for 2 dimensional, we're dealing with here a right angle triangle. And then we are saying we'll have charges like that, like that. And then we can be able to solve questions based on all of this. So I hope you are ready to deal with our 1 dimension as well as our 2 dimensions, so that you are able to answer questions. Remember, when you're dealing with F net, you will have all the forces there that you are having, and then you will be able to add the force of RT, the force because of ST as well. You're able to add them to get your F net. So we will just do the vector sum there of those. The force of R on T plus the force of S on T. So you're able to have all that, and then you are able to get your F net. And that's when they are one dimensional. But when you are dealing with this one, X, Y, Z there, you see that, okay, you're going to use a theorem of Pythagoras. So you're going to say F net squared when you're getting the F net there. It will be F net squared equals to, then you have now that F of X on Y as well squared plus F of Z on Y squared. So you're able to see that you're going now to use the theorem of Pythagoras. So you will have that force there and that force there, and then you add them. And we are saying it's a vector sum. The direction is important. If the other one is negative, the other one is positive, it will have a bearing on your F net. So you are able to do that, and then you are able to deal with your question. So you are able to know that when they're in one dimension, you will get the F net like that. When they are at an angle or at a right angle triangle, 2 dimensions, we'll use the theorem of Pythagoras. I hope we're together, and then this will help you as and when we start dealing with questions. We have talked about Coulomb's law, we've talked about electrostatic force, but as well, we must talk about electric field. Electric field is important as well. So as I indicated, here we deal with Coulomb's law, where we are focusing on the electrostatic forces, and then now we are dealing with electric field. Electric field as part of this topic as well. To say, you must know how to describe an electric field. You must know how to describe an electric field as a region in space in which an electron charge experiences a force. A region of space or a region in space in which an electric charge experiences a force. What do you mean? You know, when you are playing, let's say you're playing soccer or cricket, whatever the sports that you like, you know that there is a field that you play inside there. Even when it comes to these charges, there is a field which is a region in space, like a ground in terms of that one. I'm just using it so that you can bring it home and have understanding of what we're talking about here. We're saying electric field is a region in space in which a charge experiences a force. So we are simply saying if the charges are far apart from one another, they have a long distance between them, they might not experience any force. But as you bring the charges closer, when you enter the region in space, then the charge will experience a force. So immediately when there is force that is experienced, we say now we've entered the electric field. I know you know the magnetic field when you're dealing with your magnets there, to say if magnets are far from each other, you won't feel anything between them. But as you bring them closer, you are able now, the north and the south pole, you're able now to see that the magnetic field is increasing as you bring them closer. So it's important that you have that understanding of what is electric field. We are saying it's a region in space in which an electric charge experiences a force. So you know that that is electric field. So that is definition number 2. The first one we've defined or we've stated Coulomb law. Now the second one we're saying the definition you must know and seeing for this question is electric field. We don't have too many definitions in this section. So we're expecting you that at least these 3 you will know, which is Coulomb state, Coulomb's law. You define electric field as we're describing it. You describe electric field as a region of space in which an electric charge experiences a force. And we are saying the direction of the electric field at a point is the direction that a positive test charge will move if it is placed at that point. I would like to explain this one so that you understand this and you are able to move together. So we are simply saying if, for example, we are having a positive charge, a positively charged sphere there, when we bring a positive test charge, another positive test charge, when we bring it closer to this positive, you know positive and positive, they will repel. So definitely is that there will be repulsion, which means from a positive sign, definitely it will be away like that. The electric field will be away because our test charge is positive. So around the positive, we have the arrows or we have the electric field that is going outward. But if we check now, if we are having a negative, when we bring a test charge that is positive, when we bring it closer there, it will be attracted. You see, which means now when you draw on this one, you will see that the arrows are towards. So you can see that negative shows attraction while positive shows repulsion. So you can see that when it's a positive charge, it will write our arrows as they are going out like that. But for a negative one, it will be towards, because a positive test charge, when it comes towards a negative, it will be attracted towards it. Hence, when we draw, you will see I have a slide that is going to show you how to draw the electric field patterns. I just wanted you to understand the statement to say, have in your mind a positive test charge. To say, as I bring a positive towards a positive, what will happen? Definitely there will be repulsion. Hence, you are seeing that the positive now will be outward, as you can see it there. But as I bring the positive test charge closer to the negative, there will be attraction. Hence, towards a negative, there will be arrows that are going inside. So if you have that understanding, when you do the electric field patterns, you will understand and will move together. And we are saying you must be able to draw these electric field patterns for a single point charge and for 2-point charges. For 2-point charges, where one is negative, the other one is positive. Or you can have both positive or both negative. So we're expecting that you know how to draw for how many? 4 electric field patterns. That is for 1 negative, 1 positive. You can be able to draw, at least I've shown you there, for positive and for negative. And then both positive. When you have both positives, you must know how to draw when you have positive and positive. And then when you have both negative, you must do that, which is what I'm going to show to you. And then you must be able as well to define, our third definition is to define electric field at a point. Electric field at a point. And we are saying you define it as the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So here it is, your definition. It is the electrostatic force experienced per unit positive charge placed at that point. So easy, from the data sheet, you have this formula. It will always remind you what is how to define electric field at a point. So we're saying electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. So get this mark for definition. So either we'll say state Coulomb's law, define electric field at a point. When it comes to electric field, we said always have a positive test charge in your mind. To say, as I bring a positive test charge, what will be the interaction between positive and positive? We said it will be away because there will be repulsion. Between positive and negative, it will be attraction towards, hence you will draw it like that. So you have that as you draw your electric field patterns. And then we're saying electric field at a point, we said is the electrostatic force experienced per unit positive charge placed at that point. And then you're able to get all these definitions. I hope definitely the definitions are in your pocket and you are ready to collect them come your exams. Now, we are going to calculate the electric field at a point due to a number of charges using the equation to determine the contribution to the field due to each charge. So we're always looking for the contribution to the field due to each charge. So you can see, unlike we're not doing electrostatic force because we're using both charges Q1 and Q2, and then we had to get the force of attraction or repulsion between them. Now on this one, we are looking at the contribution of each charge. So we only have one charge in our equation because we deal with them individually, these charges. Hence, we have our formula for electric field as E equals to KQ over R squared because we want the contribution of each charge. So don't make a mistake of confusing the two formulas. The one for electric field, you can see, is the contribution of each charge. So we only need one Q. Hence it's saying KQ over R squared because you are dealing with the charges individually. So I hope that helps you. And as well, we're going to deal with the issue of E net, where you can be able now to add the electric field that you have calculated. Now, as promised, the electric field patterns. So these patterns, remember what I said? You must know a single point charge. We said you must know for a positive, hence you see the arrows there are outward because we are bringing a positive test charge. Hence it will repel the positive that we are bringing. But as you bring the positive charge, it will be attracted. Hence the arrows are going inside there. Then you are able to see that, okay, for a single point charge, we know for positive, when you bring a test charge, positive test charge, it repels. Hence, when you see positive, you see repulsion because you are having the positive test charge in your mind. When you see negative, you see attraction, where we're attracting the positive test charge. And then when you are having 2 point charges, unlike they must attract, then you can see the arrows from the positive there. The arrows from the positive there are outward, the repulsion towards negative, because when you bring the a positive test charge, it will be attraction. So I hope now you have the understanding to say when it's a positive and a negative, our arrows are always moved. The movement of our electric field is from positive towards negative. Then you understand it like that. If you are having a negative charge and a negative charge, 2 of them, now what happens? Like charges, they repel. So you can see that they won't be able to touch one another like that. They are able now to repel one another. But towards the positive, you can see that the positive, the arrows will always be going inside. But when it comes to 2 point charges that are positively charged, you can see there that the arrows are outward because you have the positive test charge in your mind. To say, as I bring the positive test charge towards these ones, they will definitely repel. And as you bring positive and positive closer to one another, they will definitely repel one another. So I hope you've understood the issue of electric field. And then we have emphasized the issue of electric field at a point, where we said at a point is the electrostatic force experienced per unit positive charge placed at that point. So you know electric field at a point as well. So electric field patterns, very much important. You will see when you do questions, there will be questions that are based on the electric field patterns. Now, baseline, just to check. Remember, these topics, you studied them in as early as grade 10. You were doing electrostatics there. So we just want you to remind you the basics of what you already know, to say you are not empty. In grade 11, when we went to do the topic, you did it as well in grade 10. So it's important that, hence we are saying National Senior Certificate is a 3-year course. You are doing this certificate for 3 years. It starts in grade 10, grade 11, grade 12. And if you lack the basics of grade 10, it's important if you want to build yourself and have the foundation. It's important that we even encourage you not to throw away your grade 10 books, your grade 11 books, because you will definitely be able to go there and check where the concept started so that at least you build on the foundation. And once you build your house on a firm foundation, we hope that you will enjoy these topics and you'll be able to do well. Now, let's check our baseline. The first question there was, name at least 3 ways to charge an object. So the object, how do we charge? Whether it's positively charged or negatively charged, how do we charge them? You can think about it. Now, if I'm to remind you of ways to charge, remember by rubbing. When you're rubbing a cloth, you're rubbing a ruler in your head and all that. You always, you have done that. So we are talking here, you can do that through that, which is friction. You can just use friction when you're rubbing a cloth or something against another material. And then you can do that by conduction. You can do that by induction as well. So these are some of the ways that we use and that we have done in grade 10 that tells you to say this is how we charge objects. We charge objects like that. And we can even use what is called a polarization. You can use polarization for charging of these objects. Objects can be charged like that. And then we're saying which one between the negative charge and the positive charge is transferred. Oh, a question. Which one between the negative charge and the positive charge is transferred? So this question, they are very much important. Remember, we transfer the negative charge. The negative charge is the one that is transferred. And these topics helps you as well when you are going to start and continue. Remember, you've done redox reactions in grade 11. And then there was loss of electrons and gaining of electrons. You can see everything is about the electron, which is the negative charge. Loss of electron, which when you start your redox reaction, you're going to call it oxidation, and gaining of electrons. So these signs, you must look at it holistically to say there's always somewhere where these topics, they come and meet and they talk the same language. So we know that it is the negative charge that is transferred. So the movement is the movement of the negative charge. So it is the negative charge that is transferred. Hence, I've shown you with the loss of electron and gaining of electrons. So we always talk about the electron, the negative charge. It's either it's lost or gained. Then we know that we are able to move like that. Now, on 1.3 then, we're saying when the number of electrons is equal to the number of protons. So the object is said to be negatively charged, positively charged, or neutral. So that is important as well to say when the number of electrons, remember electrons are negatively charged. When the number of negative charges and the number of protons which are positively charges, when they are equal, we are saying that now the object is neutral. So when we say the object is neutral, we're saying that the electrons, the number of electrons and the number of protons are equal. So I hope you get that. And 1.4 will help us to demonstrate what we are talking about there. 1.4 is saying, what is the charge on an atom that has lost an electron? So you can see it's all about the electron, but in a paper one way, because you will still talk about electrons in terms of paper two. But the electron is an electron. It doesn't depend whether you are doing physics or you are doing chemistry. We're talking about the same electron, which is negatively charged, and the same proton that is positively charged. Now we're saying, what is the charge on an atom that has lost an electron? So you will know that if, for example, you are having sodium, sodium is number 11 in the periodic table. So you will know that sodium has 11 electrons and 11 protons. So 11 negative charges and 11 positive charges. And sodium is written as neutral. The neutral there is telling you that the number of electrons is equal to the number of protons. So you are able now to say, okay, 11 electrons, 11 protons. But if sodium loses 1 electron, for example, it becomes positively charged. So you got to know that when a charge, what is the charge on an atom that has lost an electron? So when you see a positive, one positive, sodium plus, you know that it means that sodium has lost one electron. But when you see, for example, magnesium 2 plus, you know that that magnesium has lost 2 electrons. So you're able to see that the 2 plus is indicating the number of electrons that have been lost. Why is that like that? Is it like that? Because we are saying the number of electrons and protons are equal. So if we lose 1 electron, we're going to have, for sodium, we're going to have 11 positive charges and 10 negative charges. So you can see 11 minus 10, we're remaining with positive 1. So you are able to see that when we lose 1 electron, we'll have sodium plus. So the question was, what is the charge on an atom that has lost an electron? So we're saying the charge is positive. It will have a positive charge. When you lose electron, you gain a positive charge. When you gain electron, you get a negative charge. So which means that now when you get a sphere that is positively charged, you know that that sphere is electron deficient, is running short of electrons. But when you have a sphere that is negatively charged, you know that it has excess of electrons. It has more electrons than protons. I hope you get that, and it helps you now to move with the equation. And what I was doing, I was explaining the answer in 1.4 to say as an atom loses an electron, it becomes positively charged. I've demonstrated to say we have equal, in a neutral atom, we have equal number of electrons and protons. But immediately we lose 1 or 2 or 3 electrons, then the atom will become positively charged. It will help you, as we here, we are dealing mostly with positive charge, negative charge, and neutral. So our sphere that we'll be dealing with, they will be positive, negative, or neutral. So it's important for you to understand the meaning of a positive charge. You know, positive charge, it means that we have lost electrons. Negative charge, it means that we have excess of electrons. And neutral means the number of electrons and the number of protons are equal.